So in the last chapter, we looked at just expressions for acceleration and velocity, whether they depend on time or position, and we called that kinematics, because we weren't really talking about the forces that were responsible. In chapter 13, we're going to talk about those laws and get at the equations of motion through them. Just to remind you, one of the problems we had in the last chapter was this parachute problem. And if you remember, we were told that the acceleration of this parachute was g minus cv squared. Well, now, if we think about it from the point of view of forces, we understand that there's a force down equal to mg, and then we see that this term, which is related to this, the c's aren't the same, of course, because of the factor of mass. That's the drag term. And so what we really were doing is we were saying the sum of the forces equals the mass times acceleration, and letting down be positive, we would say the forces were mg minus big C v squared equals mass times acceleration. And then if we divide by m, we get acceleration as g minus big C over m v squared, which we could just rename that constant as a little c. All right, so you see that we're kind of going at it from a different angle. In the end, we want to find these expressions for acceleration that we can integrate in order to find more information, like how does velocity and position depend on time, or how do they relate to each other. But we're going to start from the point of view of forces to get those expressions. And as we did in the previous chapter, we're going to look at different types of coordinate systems that we can use to study different types of motion. Okay, so let's just remind ourselves of Newton's laws of motion. So the first law, a lot of times we talk about as the law of inertia. We say an object at rest, stays at rest. An object in motion stays in straight line motion and both of these things are true unless a net force acts upon the object. So we call it the law of inertia because inertia refers to an object's resistance to a change in its motion. And it's quantified by the mass. The mass is how we quantify the inertia of an object. All right, so that's just a review. The second law basically is, what if there's a net force? Because the first law is answering the question, how does an object move if there's not a net force? And then the second law answers the question, what if there is a net force acting on an object? And that's where we get F equals ma. Typically, when you're taught the second law, it's expressed like this, where we say that when an object is acted upon by a net force, the acceleration it experiences is directly proportional to the force and inversely proportional to the mass. And of course, you can see that that was just F equals ma rearranged. And the third law is commonly referred to as a law of action-reaction for every force. There is an equal and opposite. Reaction force. And so maybe if we have objects A and B, we could say there's a force that A exerts on B, but in response, there's a force that B exerts on A, and the law of action-reaction says that these two forces are equal in magnitude, but opposite in direction, and that's where that negative sign comes from. And so that's something that we learned about as well. So when we're talking about statics, the first law and the third laws kind of talk about statics, although we don't always use the third law that much. But the first law, because in that situation you don't have a net force, that's talking about the situations where you have equilibrium. And so we spent the whole first half of the semester looking at situations where there was equilibrium, most often when there was no motion. And so that's statics. And since chapter 12, we've been moving into dynamics, where we have some net force. So this represents, in this picture, all the forces added together that might be acting on the object. Sometimes we might write that as the sum of the forces, and that's usually what we're going to say. And so this is what we're going to be looking at in this chapter. So we want to just talk a little bit about some forces that we might be familiar with. So first of all, let's talk about Newton's law of gravitation. And so we're just going to do it really generally. I have mass 1 and mass 2, and they're separated by some distance. I'm going to call that distance d for now. And notice I'm measuring from the center of each one, and I'm going to have the force that one exerts. Sorry, I drew that in the wrong direction. We're going to just say that's the force that 2 exerts on 1, and then this is the force that 1 exerts on 2, because I want to draw them in the right direction, because gravity is an attractive force. And so the magnitude of this force of gravity that exists between the two objects is expressed as big G times m1, m2 over d squared, where G is the universal gravitational constant, and it's equal to 6.67 times 10 to the minus 11. That constant is a constant of proportionality, and remember that because it's small, that means that the force of gravity that exists between two objects is a weak force. If we drew, if we imagined a unit vector that goes from mass 1 towards, or a vector that goes from mass 1 to mass 2, I'm just drawing it, shouldn't have drawn it like that, but if we use a little r hat, the way that we might draw or write the force that object 1 exerts on object 2 is minus g m1 m2 over d squared times r hat. And that negative sign is because it's attractive. You might see it written in this way in your textbook, and so I wanted to write that to draw your attention to that, because when we're thinking of the force of gravity due to mass 1, we draw the vector that talks about the distance from mass 1 to mass 2. I didn't go all the way, but the unit vector is in that direction, but of course the force is in the opposite direction. Now, if you think about it, then this force of gravity helps to explain for us the force of weight. So here's U, And here's the Earth. And this is the distance, the radius of the Earth. And so the force of gravity between you and the Earth can be written, I'm just writing the magnitude right now, mass of you, mass of the Earth, and then the radius of the Earth is squared, because we measure, when we have a large object, we measure the distance between large objects from the centers, and in a sense what we're pretending is that all the mass of the Earth is concentrated right at the center, and that's how we find the distance between the Earth and you if you're standing on the surface of the Earth. Because if you think about it, if we said, oh, I'm touching the Earth, so the distance is 0, well, that doesn't work because you can't divide by 0. You'd get infinite answer. So anyway, this is how we express the force of gravity that you feel because of the Earth. And we can also set that equal to ma. And so, because it's gravity, we can call this g. And remember, we call this your weight. But now we can also call this force also is your weight. If you go to a higher altitude, if you were floating out here, we would use your height above the Earth, and so then your total distance between you and the Earth would be the radius of the Earth plus your height. And so we could see that your weight would actually begin to decrease as you moved up into the air. You'd be surprised that it's not as drastic as you might think, and that you don't go to a 0 force very quickly. All right, and so here, again, just kind of using these ideas, so remembering from the previous slide, we had your mass, the mass of the Earth, and the radius of the Earth squared, and I forgot the big G, so I'll put it right here. And so this is equal to your mass times gravity. So from here, we can actually write, the acceleration of gravity can be expressed like this. And now we see why different planets have different accelerations due to gravity, because they have planets that have different mass and different sizes. But notice that, and also remember when we talked about the fact that what if you're up in the air, your weight would be different, and so we would replace the radius of the Earth with the radius of the Earth plus your altitude. And so we see that that acceleration of gravity changes and your weight changes. So one of the things that we want to understand is your weight can change depending on where you are with respect to the Earth, and even if you're on another object, like maybe you're on the moon, or maybe you got to travel to Mars, your weight will be totally different because of the new acceleration of gravity that you experience. However, your mass does not change. So just remembering some of the things that we are familiar with, because mass and weight is kind of different if we use the metric system and if we use our normal English system, the foot, pounds, and seconds. Because in the metric system, we measure mass in kilograms and we measure weight in newtons. And a lot of times it turns out that when you're told about an object, you're actually given its mass. Like you might say, oh, this thing has a mass of 200 kilograms or 5 kilograms, or something like that. And then you'll always multiply it by the acceleration of gravity to get its weight. It's a little bit different in our units. We're actually used to using units, like when we're talking about an object, we actually talk about its weight, like it is this many pounds, or it's 2,000 pounds, or it's 5 pounds. But then that's not telling us its mass, that's telling us its weight. It turns out that we'd have to divide by the acceleration of gravity to find its mass, where the acceleration of gravity in our system is 32.2 feet per second squared. And what might surprise you is what are the units of mass in our unit, in our foot-pounds and seconds system, and it's slugs. And you know that I don't know when I've ever seen something given in terms of slugs. It's always given in pounds. And so that's kind of interesting, the difference between those two systems. So finally, we're getting back to what we're really going to focus on in this chapter is finding what we call the equation of motion for an object, where basically the way that we're going to work at it is, in the end, we want to know what this acceleration of the object is so that we can work with that and find more information about the motion of the object. But the way that we're going to do that is through Newton's second law. And so we're going to first identify these forces and add them all up, and then set that equal to mass times acceleration, and then go from there. Keep in mind that when we're adding the forces, remember the forces are vectors. And so we will break this expression down into components. And as we go through the chapter, we'll start off with x, y, and z components. And so we'll look at the sum of the forces in the x direction equals the mass times the x acceleration. Sum of the forces in the y direction equals the mass times the y acceleration. But then we will also add to our repertoire, which we have learned about in the previous chapter. We'll sometimes look at tangential forces and normal forces. We'll look at forces in terms of polar coordinates, cylindrical coordinates. So we're going to really kind of be a little bit more expansive and do a little bit more than you've seen before in general physics.